Cables. 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 Gosh, Thomas, you have so many cables. Yes, I do. In fact, here's one more. Let's talk about it. You remember my trusty dusty server rack, right? Here's my PC. We talked a lot about this already. Here's my wimpy 2 hard drive NAS. That's just a Dell R210 too. It doesn't have the most, I bit my tongue. It doesn't have the most storage capacity out there, no. But it isn't the fastest. But I think we can change that today. So I want to talk to you about networking. My home network is pretty interesting. I have a pfSense firewall that gets internet from my internet connection and splits it out to 4 subnets. I have one subnet that's for this puppy right here. My entire battle station is one subnet. I have another subnet for my Kubernetes cluster. I have another subnet for my electronics workbench, and I have a final subnet for my work computer setup. And I also have a bunch of VLANs too, because I really don't like IoT devices talking to each other. So I have a VLAN setup that connects my lights. Turn on the lights. There, I think that's out of frame, but you get the idea. I have one for the lights, one for the Amazon Alexa, and that 4th subnet is for my work computer because I don't want them talking to each other. I don't like that. Stop that. I hate that. I hate it. I hate when IoT companies are like, oh, we're just gonna look around your network and find your other devices. No big deal. It is a big deal. Stop that. Stop it. Please. Before I get too carried away, right, the cable. I brought up the cable. This is a really cool cable because these are not RJ45 jacks. They are not Ethernet. This is not an Ethernet cable. It's something a little different. And to connect the cables, I need a pair of these. These are also very interesting. And I want to talk to you about that, but first I want to address the problem that I'm trying to solve. On my PC, I prefer to edit videos with the files directly stored on my storage server. So when Premiere's running, it's reading the files from that storage server, which introduces, of course, a network bottleneck. All of the computers in my rack right here are connected to one 1 gigabit capable switch. And that switch goes all the way back over like a 50-foot Ethernet run to my pfSense router. So the files in my storage server actually have to go through a switch all the way back to my router, and then the router says, here's the host that I want to connect to. And then it goes all the way back to the switch and then to my PC. It introduces a ton of latency. In fact, I'm going to show you just how much latency. So an IP config reveals that my IP address on this machine is 192.168.1.111. Very cool. Now I know that my TrueNAS server is the same subnet but 1.5, so let's ping it. 192.168.1.5. There we go. Okay, so it did pretty well. Very, very high scores here, but this is on the order of milliseconds. I want to see nanoseconds. So let's see how we do that. I'm going to show you another utility that you can use in Windows. This is open source software, so it's not included by default, but it's called HR ping, and it's very cool. So I'm going to HR ping my host, and what this will do is it will actually show us the time in nanoseconds. So you can see 0.337 milliseconds. In nanoseconds, it's 337 nanoseconds. So this will give us a whole lot more of a granular view of what the response actually looks like. So this shows you that, the average is about 346 nanoseconds to get from my PC to my NAS, which you'd think that's really, really fast, which it is. But we can actually do a whole lot better. All right, I'm going to show you a different way. So these are all the files that I used to make the last video, and I'm going to take them from local storage. They're stored in my SSD right now, and I'm going to put them on the NAS. And let's see what happens. So about 50 gigabytes remaining, and this transfer speed, it spiked a little bit, but we see we're settling in around, 100 megabytes per second. And keep in mind that 100 megabytes per second, that's 1 gigabit. So this is being transferred at the absolute maximum speed that it can be transferred, which is really good. It's doing very well. But that's still 50 gigabytes. That's still going to take quite a while to complete. Yeah, and this is what I'm talking about. The speed, all right, it's back up now, but it just dropped to 2 megabytes per second. Whoa, hello. Oh, man. Okay, we're gonna replace files, yep. And I don't know if you can hear, but the fans are starting to go wild. Listen to this. They're not enjoying this file transfer. Oh. And the hard drive light just stays on. Let's talk about why this, a direct attached copper cable, might do better than this, your standard Cat6a Ethernet cable, in terms of latency. And luckily, FS Cables, who provided this cable for me for this video, have a really good article about this very subject. And I'm going to plug all of the references that I used for this video in the description so you can check them out yourself. Let's start by talking about the Ethernet protocol. So data is sent and received in these little packets, these little chunks of data, and these chunks sort of look like this. They start with the header, and this is purely for syncing clocks between machines, and then the destination MAC address is specified, the source MAC address is specified, and then the data frame type. So this entire block here is data, and this specifies the format that it's going to be presented in so that the receiving computer can interpret it. And then finally, there's a little block on the end for error checking, because Ethernet does check for errors. And these errors could be anything like missing data, data that has been altered in transmission, stuff like that. And the reason why this is important to me here is because traditionally what I've been doing is I have, one PC, another PC, and then I have a switch, right? 1 gigabit switch, that's my switch. And then I have a router. I don't know if there's a better way to draw this, but that's my router. I'm gonna give you PF sense. Yeah, that'll make it more clear. So if I want my machine 1 to communicate with a second machine, what it's doing is it's coming here, going to a switch. The switch goes back to a router. The router comes back here and redirects to the second machine. And the reason why this is important is because when the computer wants to send data, every system along this line needs this information to figure out where the data is going. So the pfSense box is going to listen to this signal and say, okay, source is this computer and the destination needs to be this computer. So it has to make that translation, and it also happens at the switch too, because remember, there's a ton of devices connected to my switch. The switch needs to figure out which device to send information to. And this process, it happens very, very, very fast, but it's not instantaneous. So the more steps like this you have, the more latency you introduce to the system. So instead what I'm doing two things. The first is the 1 gigabit. No, we're gonna go 10 gigabit per second. My handwriting's terrible. We're going from 1 gigabit to 10 gigabit. It's going to be really cool. But the other thing that we're doing, we're not going through this whole step here. We're not doing this whole process. We're going to go from one machine directly to the next machine. And we're not doing this over RJ45 Ethernet. We're doing it over direct attached copper. And this direct attached copper will follow the SFP Plus protocol, which these, in essence, if you're looking at IEEE standards, there's not much difference in the actual data transmission protocol, but the difference, of course, is in the signaling. In this cable, a traditional Ethernet cable, you know, your Cat 5, 6s, 7s, all of that stuff, there are 8 twisted pair connectors. Let me get you an open cable to show you. They look something like this. So you see there, these twisted cables. This, by the way, is Cat 6A cable. There's a bit of shielding in here. These wires are shielded. And it looks like this. But pretty much with each of these pairs, data is being sent through both of the cables, and it's being done inversely. So if we actually look at the signal, here, let me whiteboard this. So within these twisted pair connectors, there's 2 pairs. Here I'm going to draw 1 pair, another pair, another pair, another pair. There's 2 pairs in the cable that are transmitting data, and these 2 are for things like power and whatever else is needed to effectively use the Ethernet cables. But these 2 cables are sending data, and the way they do it to avoid electromagnetic interference is in one cable. Here I'm going to do it like this. In one cable, the data is going to be sent probably like this, you know, high, low, some low, high. And if you sync the time, which is another function of the other 2 pairs, these happen kind of like this, right? And I can mimic the time on the other cable in the same twisted pair. Remember, this is the same twisted pair cable. 1 conductor here, 1 conductor here. And what's happening here is this is high, low, high again, low again, high for some time, and then low, and so on and so forth. Oh, I forgot to draw a little line there, but you get the idea. The signal that's going to be transmitted in each pair is alternating with itself. And that reduces the electromagnetic interference, because remember, when you send electricity through a wire, you're going to generate a magnetic current. If you send the opposite signal, you're going to cancel that out. It's very interesting. But like I was saying before, all of these steps with actually taking data from the source, and the network interface card has to translate that into electrical signals, and then the other network interface card has to take those electrical signals and translate them back into data. That takes a lot of time. And the process by which it does that is a little old. In contrast, the SFP Plus, or the direct attached copper cable, it's a little simpler than that. There's actually only 3 conductors. There are 2 data conductors, or 2 data lines, and then a copper shrouding around the whole bunch that is for resisting electromagnetic interference. By using direct attached copper like this, well, here's the deal. You can use RJ45 for 10 gigabit Ethernet, no problem, but you can't really do much more than that, and that's just a factor of the electromagnetic interference. So Ethernet runs, they can go pretty far. You can go 100 meters, maybe some more, no problem. But if you were to try to go farther than that, you're going to have a bad time, and there's going to be a lot of errors because that signal cannot keep going for that long. In data centers, you would turn to something like this, because this standard, the SFP Plus standard, can use fiber optic cables. There are little transceiver modules that fit in here that turn the electrical signals that are generated by the controller on board to light signals. And that light can travel really, really far. You can connect buildings with this stuff. And with SFP Plus, you also give yourself the overhead to handle much faster, higher bandwidth transmissions. So you can go well beyond 10 gigabit in that scenario. And as far as connecting the computers together, that's why I have 2 of them. One of these is going to go in my PC, the other one is going to go into my NAS. And what I'm going to do is I'm going to create an ad hoc network. This is just a small little network. There's no router involved, there's no switch, no firewall. It's just one computer talks to the other computer on its own dedicated network. Let's put it together. All right. For all intents and purposes, this should be the most difficult part of this process. I can just slide out this server, I turn it off, slide it out, put the network card in, push it back, all is good. This one's not on rails, so I have to take it like completely out. What, do you think I was gonna pull the rack out to make it easier for myself? Who do you think I am? By the way, my tripod's still not fixed. I haven't bought a new one, it's still taped. If you want to support me on Patreon, get me a new one, I would greatly appreciate that. Now let me show you why I love rack mount servers so much. Just look at this. Boom. Just like that, it's out and ready to work on. So I've pulled out the bracket from here, and this kind of just will go right down in here, so I will line it up. Pull this out the way just for a second. Line this up, and there it is. That's lined up all right. And it's clicked, and that goes down there. Just like that, we've got 10 gig. But of course, I still have to take this guy out, so here we go. Oh, that's heavy. Oh. Yeah, it is a little dusty. It's not what you like to see. Oh well. Now I will need to do a little bit of surgery here. This metal bar is actually here, by the way, I didn't explain this in my computer video. This is here to add a little bit more rigidity to the case so it doesn't bend components. Very handy to have. I think my concern here is just that this might put the card too close to the intake fans, but now that I'm looking at it, it seems like that won't be a problem. And it is always best practice to try and keep cards close to the top of the board, like closer that way, because they're more likely to be directly connected to the CPU's PCIe lanes, which is good practice for speed. But this looks good, so just pop that down there. Oh, I see a problem. Okay, so this part, this little metal bracket, hits the SSD heatsink, so I'm gonna have to take that off. Luckily, there isn't an SSD down there though, so this isn't a problem. Although what is a problem is the screws are really small. All right, new plan. It's gonna go in here. I can't get this heatsink off, and I'm gonna stop trying and try not to, you know, destroy the board. But you know what? That's enough space. That'll be fine. Let's put this back together. Oh, yeah, I do back to front. Got it. Ah, we meet again. Yes. I'm just down here putting in the cables. You know how it is. We have one more cable to put in here. Let me get the wraps off of it. So you'll see that there's some ports. This is probably not the best thing. Let me move you. Welcome below the desk. So here's what the connector looks like, and you'll see that there's like some circuit board. There's a bit of connector down there. This side faces the PCB of the network card. So this will kind of plug in just like that to my PC, and then I'm gonna go to the other side to connect the NAS up. Oh God. Okay. No. Whoa, Thomas, is that your server rack? You're so cool. Must be easy to work on that thing, isn't it? Yeah, it's super easy. Oh, okay. All right, no, you know what? Okay. Oh, I got it. Oh, you're almost there. Oh my God, okay. All right, let's go configure an ad hoc network. Now, I have to admit, the process of setting up the ad hoc network was neither fun nor enjoyable, and this is usually why I stick with hardware, because it's so much more fun and genuinely easier than software. We're also dealing with Windows versus BSD, which, and I got it working ultimately, so that's what matters. So the process kind of went a little something like this. I hopped into Windows and I set up the drivers for the new network card, the X520 drivers from Intel, and I went directly to Intel. Do not install drivers from any website that is not the manufacturer of the device. That's very important. Don't do that. And with the drivers installed and Windows recognizing the card, I went into the Network and Sharing Center in the control panel, and I basically configured a few things here for that new network. The first thing I did was set the MTU size to 9014, and that allows for large packets to be transmitted over that connection, which if you don't do that, your bandwidth will be very limited, so make sure that you enable that. And then the next thing I did was I set up a static IPv4 address. In this case, I used 192.168.100.2 because 192.168.100.1 is going to be for the TrueNAS server. With that configured, I went over to TrueNAS, and I have to admit I fumbled around a lot in the web UI trying to get the interface set up, but that didn't work. None of that worked. Nothing I tried worked there. So I actually had to go to the TrueNAS console, like the one out in the screen, like, you know, that one. I had to go to this one. And then from there, I just configured a static IPv4 address with 192.168.100.1, like I said before. And the subnet mask for these are, it's both a /24 CIDR block, so that's your standard 255.255.255.0 subnet mask, so that's also important. And remember, it's just an ad hoc network, two computers connected to each other. There's no DHCP service. There's none of that. It's not, you know, we're looking up addresses to add to a block of IP address. No, we're not doing that. Static all the way. And with that configured, I finally set up my network share in Windows. So I deleted the old one and then added the new one. But with that out of the way, let's finally do a speed test and see what we've accomplished. So what I have here is another project, an entire project, my taser box video, which if you haven't seen that, go ahead and give it a try. It's a little electronics, but you know, that's all right. I want to go to properties, and we see that this is 27.5 gigabytes. It's 218 files. It's a lot of data. So Control A, and we are going to go over here, and I'm going to copy it from my storage server to the desktop. And I'm going to say, alrighty. Oh, how's our speed doing? Not so well. I'm gonna give that a second, see if it ever comes up any faster than that. All right, well, we finished, and the results are slightly disappointing, but there's an explanation. So for that file transfer, it peaked at about 200 megabytes per second, which is still double the 100 megabytes per second that we were seeing with the 1 gigabit network in place. A big thing to remember here is that the network speed isn't the only bottleneck that could potentially be in the way. Number one, I'm writing to a very undersized machine. There's no swap partition, there's no caching array, there's nothing like that to help speed up reading and writing data. And on top of that, I'm writing to SATA drives. So it sounds upsetting, but this is about the speed that I was expecting. It's not crazy. At some point in the future, when my wallet's a little deeper, hopefully, I will build a new NAS. I will build a new TrueNAS box and try and maybe have some SSD storage, NVMe, who knows. That will yield much, much better results. But as far as this test goes, it's all right. It's not ideal, but it's pretty good. What I actually wanted to show you was latency as well as bandwidth. So remember, bandwidth is how much, latency is how fast. And what I intend to do with this server is use it as my editing server. So I want my files to live on the NAS where there's redundancy, and then I just want to use my PC to edit them. So Here is a file, this is a video file that's taken directly from the NAS. That's where it's reading it from. And look at the skimming quality on that. And this is at a quarter resolution, but that's still pretty good. Much better than what I had before, I'll tell you that much. So before, what I did was I read from my NAS to my PC and I transferred those files to my PC, but now I want to go the other way. So right now I'm transferring the files that I just downloaded locally, and I'm putting them back into the NAS, and I'm going to look at a couple of things here. I want to look at memory usage and CPU utilization. And you can see that performance has totally tanked, and it's awful, it's not good. But I want you to notice something. The CPU, it's not really doing too much. And why might that be? Look at the memory. The memory is being completely used up. And the ZFS cache, I say Z because that's what Linus says and that's how I learned all this stuff. The ZFS cache is completely taken up. The services have taken over, and that is what's really hemorrhaging our bandwidth here. So heed me when I say that network speed is not the only factor. The entire system has to be looked at holistically. So this is really the best I can do right now, but what I can say is that in the future, I'll at least not have a network bottleneck. I know that my network will be able to perform really well. This will all be a thing of the past. This will be just fine. Now, while this is finishing up, I want to take another moment to thank FS Cables. They provide me with that direct attached copper cable that I'm using right now, and I'm very grateful for their support. They make a whole lot of really cool enterprise networking equipment that I hope to one day have in my rack. And I hope you also appreciated this take on networking. I hope it's not as boring as networking tends to be. It happens, you know, networking is kind of that way. It is what it is. But if you're still here, that probably means that you're pretty excited about this stuff, and so am I. So thanks for sticking around, and I'll see you in the next one. It's gonna keep waving. I'm just gonna keep waving. Bye-bye. Check out the other videos. Bye-bye. Patreon. Give me money. Patreon.